Now is a good time to introduce two somewhat trivial topologies. These topologies are often used to produce counterexamples to certain topological claims. And we don't use them for much else, honestly. They're kind of pathological, but they provide good examples. So one topology, if you're given a set, one topology you could consider is the power set of X. The power set being the collection of all subsets. This is called the discrete topology on X. And the way you should think about it is, well, remember tau is the collection of all open sets. Here we're saying every subset of X is an open set. So let's write that down. All subsets are open. So it's kind of extreme. We use the term discrete because in particular, that means that every singleton is open. So if you took the point, just, the point A, that would be an open set. And the point B would be its own open set. And of course, unions of those and just any set you could come up with, any subset is going to be open. But it's called discrete because the individual points themselves form open sets. Whereas on the other hand, if you go in the exact opposite direction and consider a sort of minimal list of open sets, then you get the indiscrete topology. So here only the empty set and the whole space are open. So I'll say no subsets are open, except those that have to be. Right. The topology always requires that these two are open. So this is the minimal collection of open sets that we can use to form a topology. And we call it indiscrete in the sense that it's sort of just on the opposite end of the spectrum from the discrete topology. It's a little tricky to build intuition for these two concepts, but you can recall the discrete metric from your knowledge of metric spaces. If you don't remember that, that's the metric that tells you that 2 points are distance 1 if the points are different from one another, and distance 0 if they're the same point. That second condition is required by all distance metrics. And a point is always distance 0 from itself, so that's required. But yeah, the discrete metric says if you take two different points, here I just have a 3-point space, I'm saying all of them are distance 1 apart. So it's easy to draw that here as sort of an equilateral triangle. Of course, you could have more than 3 points and you could still define the discrete metric and therefore the discrete topology. You could have uncountably many points and still put the discrete topology on that set. But it gets harder to draw in a reasonable way. You'd almost have to do things in like hyperbolic space or something if you wanted to represent it accurately. But that's not important. The important thing is the discrete metric here induces the discrete topology in the sense that, I'll erase these. Actually, yeah, let's keep them in. We'll just make straight lines instead of arrows. So this metric induces the topology in the sense that, well, if I think about any open ball of radius less than or equal to 1, so I don't know, let's look at this open ball around A. So that's radius 1. Then certainly, okay, that's a valid open ball around A, and it only contains A. So that open ball is the subset singleton A. And that's open, right? Open balls are always open. So here we have that every singleton is open. right? I could have equivalently drawn one around B. Or one around C. And each of those would be open, and just like I drew above, whenever you have the fact that all singletons are open sets, you get the discrete topology, because then you can take arbitrary unions of those singletons and get whatever subset you want. So that's where the discrete topology comes from, is this discrete metric. And the way to think about it, you can actually sort of think about it in terms of distance. And maybe that's not surprising since I'm talking about a metric here. But the whole point of a topological space is to throw away the metric, right? A topological space is sort of a metric space without the notion of distance. And the reason we like topological spaces is we can define a topology, we can define what it means to be an open set in whatever way we want to be useful for the problem we're working on. But in most cases, we like to think about open sets somehow representing distance, somehow trying to recover that notion of distance, even though we threw away the metric. And the way it works in the discrete topology is you think here, well, all points can be distinguished, right? I could put an open ball around any individual point, and that sort of separates it from the rest of the space. And so in some way, applying the discrete topology to a space tells you that no 2 points are close together, no 2 distinct points. Right? The only time 2 points are close is if they're the same point. Okay, so in the discrete topology, things really are discrete. You can look at individual points, you can put open sets around them, you can identify them and distinguish them individually. In the indiscrete topology, on the other hand, well, the only open sets are the empty set in the whole space, right? So if I were to draw the indiscrete topology, say, I don't know, I'll put a bunch of points in, doesn't matter. So there's X with the indiscrete topology, but okay, first of all, you can't really talk about distance here. It turns out the indiscrete topology is not even metrizable. There's no metric you could put on the indiscrete topology to make it into a metric space. And that sort of tells you that, okay, I have no notion of distance whatsoever, right? I can't even recover some analog of that notion, since my only open sets are the empty set in the whole space. Right? If I look at any 2 points, how can I tell that this point is quote unquote closer to that point than say this point, right? In a metric space, you could actually measure the distance. In some other topological space, you might be like, oh yeah, there's some open set here and there's some open set here, and have some way to talk about distance. But in the indiscrete topology, guess what? If you want an open set containing any pair of these points, you got to take the whole space. And so there's no way to tell like how close one point is to another. There's no way to distinguish one point from another. It's the exact opposite of the discrete topology, where everything could be distinguished. Here it's just kind of a cluster of points with no structure to it. Like I said, you can't even try to put a metric on something like that. Okay, so that's our notion of discrete and indiscrete topologies. These are the weird ones. We'll see some less weird examples as we move on. Thanks for watching.